How can we solve this integral? This antiderivative is non-elementary, meaning we cannot express the result in terms of any of the functions we know. So we can't really find an exact solution to this. Instead, we'll integrate it numerically. We'll use two methods. Method 1 is the Taylor series expansion. We know that the series expansion for sine x is the following. We have sine x squared, so we'll just replace x by x squared. And then using laws of indices, we'll multiply the powers like that. So we have the series expansion for sine x squared. And these are the first few terms. So if we want to integrate sine x squared, we can integrate this infinite polynomial. But of course, we can't really integrate infinitely many terms, so we'll have to keep the first few terms. Let's keep these four. Integrating this polynomial is of course very easy. And we'll plug in the bounds 0 and root pi. The result will be the following. And this evaluates to approximately 0.8877. So that's the result using Taylor series. Method 2 is the trapezoid rule. If we were to sketch a graph of sine x squared, it will look something like this. My sketch is not the best, but this gives you the idea. So the integral from 0 to radical pi is the area under the graph. And we can approximate this area with trapezoids. So we'll draw 3 vertical lines like this. And then connecting them will give us 4 trapezoids. 1, 2, 3, and 4. So the area of a trapezoid is of course the average base length times height, and we can use that to approximate this shaded area. We'll have root pi over 4 times the function evaluation at these 3 middle points. Luckily, the first point and last point evaluate to 0, so that makes our life easier. Substituting, we get the following, and this evaluates to approximately 0.8344. So this is the result using the trapezoid rule. We can see that it's a little bit close to the result with the Taylor series expansion, but one of them is a little bit more accurate. Which of these two methods is your preference? And do you have any other methods in mind? Because we only showed two methods, and there are multiple other ways to numerically solve this integral. So let me know if you have any alternatives.